Imagine drifting alone through the vacuum of space, far beyond the edges of our solar system. Ahead of you, the starlight begins to warp around the edges, bending around a sphere of absolute, creeping darkness. You are approaching a region where the fabric of space and time itself collapses inward. The gravitational pull here is so intense that nothing, not even light traveling at nearly 300,000 kilometers per second, can escape its grip. To cross the boundary into that darkness is to take a one-way trip into the most extreme physical environment in the universe. There is no turning back. To understand what you are falling into, we have to look back millions of years. This void began as a massive star, burning through its vast reserves of hydrogen and helium fuel. For most of its life, a star maintains a delicate physical balance. The nuclear fusion at its core pushes energy outward, while its immense mass pulls inward. But when that fuel finally runs out, the outward pressure vanishes. Gravity takes over completely. The star collapses in on itself in a fraction of a second, triggering a shockwave that violently blasts its outer layers into space. What remains is a core so tightly compressed that a mass several times that of our sun is crushed into a space practically measuring zero volume. The star is gone, leaving behind an object defined entirely by a relentless gravitational pull. There are millions of these standard stellar mass black holes scattered throughout our galaxy, but if you were to approach one of them, your journey would end almost immediately. We need a different target, a supermassive black hole. With a stellar black hole, the diameter is incredibly small, perhaps only 50 kilometers across. Because of this tight circumference, the gravitational gradient is razor sharp. The pull on your feet would be millions of times stronger than the pull on your head, tearing you apart before reaching the darkness. Supermassive black holes exist on a completely different scale. They contain the mass of millions of suns combined, fitting into a diameter roughly the size of our solar system. You will find them sitting quietly at the center of nearly every major galaxy, including our own. Because of their immense size, the change in gravity as you approach is much more gradual. If you want to survive long enough to witness the edge of the abyss, this is the one you have to choose. As you resume your descent, you are greeted by a blinding ring of gas and stardust orbiting the void at blistering speeds. The friction heats this debris to millions of degrees, causing it to emit intense electromagnetic radiation, primarily X-rays. This is the accretion disk. Looking from the side, the flat disk forms an optical halo. Extreme gravity arcs light from the back, over the top. The ring is brighter on one side because Doppler beaming amplifies light rapidly moving toward you. We can see this exact physical behavior in the very first image humanity ever captured of a black hole. Notice the distinct asymmetrical concentration of light clustered along the bottom edge, revealing the specific direction the gas is rotating. Here, immense mass dictates the rules. It twists the physical gas and dust and forces the literal pathways of light to bend, distorting the visual fabric of reality. To comprehend the final stages of the fall, we rely on the framework established by Albert Einstein in 1915, the general theory of relativity. Einstein proved that gravity bends the literal mesh of space and time. This curvature dictates that the stronger the gravitational force you experience, the slower time passes for you relative to an observer on Earth, a phenomenon known as gravitational time dilation. Inside your spacecraft, your watch ticks normally, your heartbeat feels standard. But if someone on Earth were watching you through a powerful telescope, they would see your physical movements slow to an agonizing crawl until you appeared completely frozen in place. Plunging further inward, you hit the very last ring of light before the absolute darkness. This is the photon sphere. This diagram shows a photon traveling near the center. The gravitational pull is precisely calibrated, so light neither escapes nor falls inside. It is trapped in a continuous circular orbit. Theoretically, you could see the back of your own head. On the precipice of the abyss, the universe stops functioning normally. Both time and light are captured in endless, agonizing loops. Finally, you reach the boundary, the event horizon. Once you cross this threshold, the required escape velocity exceeds the speed of light. Nothing leaves. Inside, your body is subjected to a mechanical process known as spaghettification. The gravitational pull becomes so overwhelmingly uneven that the matter making up your body and your ship is infinitely stretched and compressed into a single vertical string of atoms. Those atoms are pulled toward the very center of the black hole, a point known as the singularity. This is a region where the curvature of space-time becomes infinite. Hollywood films often imagine this center as a tesseract or a five-dimensional portal where you can manipulate time and communicate with the past. The math tells a different story. At the singularity, our current models of physics collapse. This region marks the terminal annihilation of matter and the end of the physical laws we use to navigate the universe. Back safely on Earth, looking up at the night sky, there is no need for panic. Black holes do not act like cosmic vacuum cleaners, wandering through space indiscriminately, sucking up everything in their path. As long as planetary bodies and star systems maintain a safe distance, they simply orbit a black hole in the exact same way our Earth orbits the Sun. They are the extreme limits of our universe. Brutally deadly if you cross their boundary, but acting as the massive, silent anchors that hold entire galaxies together.